Hello, my name is Igor Konnov. I'm working at Informal Systems, and I'm going to give you the first part of this talk on type inference for TLA Plus in Apalache. The second part will be given by Jure Kukovec, who is finishing his PhD thesis at UVin. So we decided to split this job of recording the video. That's why I have basically two talks for the price of one. So the title says we do type inference in Apalache. If you haven't seen this tool, you can go on the Apalache webpage on GitHub. That's a symbolic model checker for TLA Plus we are developing at Informal Systems, and we have been developing at UVin. In a nutshell, we have been developing this model checker for about 5 years. It reduces the verification questions to SMT solving, and we have been focusing on application of this model checker in the context of fault-tolerant distributed algorithms and blockchains. That's what we're doing at Informal Systems now. If you want to find more information about how it's working, you can check that UPSLO paper that is mentioned on the slide. However, this talk is not about the model checker, although that's a very interesting topic for me. This talk is about how you go from an untyped language like TLA Plus to a typed language like SMT, because SMT solvers require typed encodings. So essentially, this talk is about how you type an untyped language. And in this talk, we are going to present you two tools. One is the type checker, the new type checker we have, and another one is a type inference tool. So the type checker is planned for the next release. It's working now, and that's some local analysis of operator definitions. And if it cannot do the work, it asks the user to give it some annotations. And type infer doesn't require any annotations. It does a global analysis of the specification. However, it's much harder to make it a robust tool. That's why it's still a prototype. It's actually working, but it will take a bit more time to make it a tool that would be used for a wider audience. And what's important here that both tools are completely independent of the model checker. So you don't have to understand the model checker, you don't have to use the model checker in order to do type inference with these tools. So let's talk about the type checker. I will focus on it, and Jure will talk about the type inference. Okay, let's have a quick demo here. I will show you how the type checker is working on a simple example, which is called car talk puzzle. I took it from the repository of the TLA specifications. You can look at the specification yourself, and if you look at it, you will see that there are some non-trivial definitions that use recursion, that use functions, sets, and it's not always clear what the arguments of the operators are doing until you read the documentation, until you read the comments here. Let's see what our type checker can tell us about the specification. We'll just run the type checker without writing any annotations and see where it complains about the specification. So it complains in line 51 here. It says that it found a polymorphic type, basically some constant, and it asks us to give a concrete type here. We don't allow polymorphic types in user-defined operators, although TLA operators are obviously polymorphic. So what's going on here? We have the choose operator that just provides some element of a set. And of course, the type checker cannot figure out the exact type. What we can do here, we can define the signature of this operator sum. And in order to do that, I will have to extend the module typing. That's a standard Apalache module. And to write a type annotation. That's how we do it now. I will just copy this type annotation from my cheat sheet, because I figured out the types before. What we say here is that the operator sum is taking a function of integers to integers, and it's taking a set of integers. As a result, it returns an integer. So that's our syntax for operators. Let's see if our type checker is convinced here. Yes, now it complains about another thing. It says that it doesn't know the type of P. And indeed, P is just a constant as well as N. So what we can do here, we can introduce type assumptions. I'll just say 1. And we'll write here the assumptions about the types of the parameters. So N and P are integers. Let's run the type checker again. Now it goes through, but now it complains in line 169. And here it's actually interesting. It says that it cannot choose between a function and a sequence, because B can be either a sequence or a function given the current types in this operator. It cannot figure it out. You can again help the type checker and give the concrete type for image. This time it's not so trivial. It took me a while to figure out the exact type, but it's like that. It actually takes a set of integers and again a function of integers to integers, and it again returns a set of integers. Let's run the type checker again. And now the type checker is happy. What does it mean? It means that our type checker managed to compute the types of all expressions in all operator definitions in this specification. Although we wrote just 4 type annotations here. We gave the type annotations for the parameters, and we gave type annotations for 2 operators that are actually quite tricky, and the type checker gave up on them. So that ends this small demo. Let's continue. I hope I have your attention now after that short demo. And now I'd like to explain you how this type checker is actually working. I believe it's very simple, and I think you will agree with me. So before we can do that, let's talk about the type syntax. That's actually the syntax we use for type annotations, but it also will help you in understanding how the tool is running. So first of all, we have basic types like booleans, integers, strings, and reals, nothing unexpected. We have uninterpreted types, and wait until the next slide, I will explain all this. We also have functions from some types to some types. We have sets and sequences. They are actually homogeneous in the sense that you cannot put objects of different types into a set or a sequence. However, there is an exception for records. Wait until the slide when we talk about records. There are tuples and records. And of course, there are operators that map a fixed number of arguments to the results. And there are type variables that allow us to talk about polymorphic types in type annotations and type inference. If you want to see more details, go to the Apalache repository and check this architectural decision record on types. So, uninterpreted types, I promise them to you. Often, if you look at the specification, you see constants. And these constants are often sets or just some values. And usually it actually doesn't matter whether these sets are sets of integers, booleans, strings, so on and so forth. You can see these examples in Paxos. For instance, there are sets of values, sets of acceptors. You see it in other examples like prisoners, missioners, and cannibals. In all these cases, actually, you should use uninterpreted types, because the only thing you can do about uninterpreted types is to compare objects, say, inside sets of uninterpreted types. And in this case, acceptors will be just a set of processes. We don't know what processes are. You can only say if 2 processes are equal or not. And the same applies to values. If you have seen model values in TLC, that's actually uninterpreted values. You can say that these are model values of types A, B, C, D, and so on. A, B, C, D, and so on are actually uninterpreted types in TLC. So that's how you can express the things. How does our type checker works? We say it's embarrassingly simple. Let's see if I convince you. So first of all, before the type checker can work, we should annotate all the built-in operators with some signatures, operator signatures. Plenty of TLA operators are quite simple in that sense. Say arithmetic operators take two integers and return an integer. Some operators are also kind of simple, but they're polymorphic. They're also very adic here. For instance, set constructors take several elements and return a set of those elements. Say if there are two elements, we return a set of the same type. You can argue that in TLA, set elements might have different types, yes, but not in our type system, not in our type checker. Records are a bit of an exception, you'll see it later. So several operators actually can be treated as overloaded operators. For instance, the tuple operator creates either a tuple, say in this case a pair, or a sequence of elements of the same type. Again, you can say sequences are tuples, tuples are sequences, yes. In untyped TLA, that is true, not in our type system. So we would reject some specifications that you would believe are actually okay. And there are a few hardcore operators that actually bind some values to the variables. For instance, a set filter in our system becomes this huge operator that says you have an operator that takes some type A and returns a boolean, that's a predicate. And given this predicate, it returns a set of A's. And actually what is happening here, how does it do that? It binds a name X to the elements of the set S, gives this X to P, and P has to figure out what to do about this X. We looked at all these annotations that we wanted to have and figured out that there is a very simple language that can describe all of the TLA operators if you think about them in terms of a type system. That's what we call a simple lambda calculus over types. It has just 6 constructs that we see here. First of all, you can have a type, that's obvious, right? You just have a type like int or a function from ints to ints. You can have a variable name, you can have lambda abstraction, as you have seen on the previous slide, just binds the variables x1 to xk to the elements of the sets that are presented by the expressions e1 to ek. And these names can be used inside the expression e. The let definition, not surprisingly, binds the expression e1 to the name x, and this name x can be used inside the expression e2. The application by name, like if you have a user-defined operator, you just take the operator name and apply it to the arguments e1 to ek. And the most interesting case here is, of course, the application by type. Here you have a choice of types, operator types to choose from, and you apply one of these operators to the arguments e1 to ek. It's a very simple language, right? Much simpler than TLA. However, we can translate every TLA expression, all the built-in operators and user-defined operators into this simple language. What can we do about this simple language? Well, we can take an expression in this language and infer the types by doing equation solving. I just show you an example here. Here is a TLA operator, a very simple one, right? We translate it into our calculus. You have a lambda expression with a signature int into bool, and you pass x and int. What do you do then? Well, you make equations, introduce equations. For this operator, for this let expression, you say there is a type A1. It should have this shape because I know there is lambda inside. And for the lambda, I know that this expression should be a set. So I say A4 is a set, and it has this shape, and actually it happens to be equal to set of A, because what else can we do here? And A2 expresses the elements that are going to be bound to X. Then you jump inside this expression. You see an operator application here. You know the number of arguments. So you say it's A5. It has 2 arguments and returns A3. What are these arguments? Well, they have to be equal to the value of X, and X is encoded by the variable A2. And the second argument is int, this we know, right? And we have the signatures, so this operator actually has to match the signature as well. We solve these equations, we have the answer. Well, I was using this kind of special squiggly equality. It's not exactly the equality. What we mean by this, it's unification. In basic cases like ints and ints, we just say they're equal, like terms. If you have variables, unification can say whether they're equal or not, and return a binding as a result. Or in this case, we can have two bindings. We solve some of the equations here. And the most interesting case here is records. We actually can unify records that have a different number of fields. In this case, we would produce a joint record that has all these fields that are unified. But we don't allow to unify records that have that assign types, different types to the same name. So in this way, we can have records of different types mixed into the same set, like you can see in Paxos, but we still stay relatively precise in our type checking. And as a side effect, since we solve equations over type unification, we can do some local type inference. So there are some boundaries of this type checking, and I think it's actually quite good for the user to understand what's going on. We limit type computation to operator boundaries if a type checker cannot find the types precisely within a let definition or operator definition just fails, as we have seen. We don't allow polymorphism in user-defined operators, and that's actually a very good topic for the meeting to discuss. And at the same time, we allow polymorphic, monomorphic, and overloaded built-in operators. Otherwise, we wouldn't be able to do the type checking. So that finishes my part about the type checker, and now Jure continues with type inference.
All right. Hello, everyone. Welcome to this part of the talk where we discuss type inference in TLA. So this talk is going to be about 5 things roughly. First is going to be about our type system and practice. I'm going to walk you through some examples and of course some of the experiments we've done. And then I'll talk a bit more about the behind the scenes, the theory, how we actually do this at the first order logic level, how we encode type systems, and then finally how we encode types of TLA expressions. So here's what we do at a conceptual level. So first, we use the TLA specification to get some bounds information. So we're not going to use all of the types in the type system. For a concrete specification, we only have to care about a finite number of them, specifically finitely many records and tuples. It's going to simplify a lot of things. Then we take the specification or any sub-expression we're interested in, and we create the SMT constraints from that expression's syntax tree. And then we have two options. Either we have a satisfiable set of constraints, we get a model, and from that model we reconstruct the types, maybe with some post-processing where we make this more user-presentable, or alternatively we have a type error, in which case the user has to go and fix the specification. All right, so let's walk through an example. So here's a very simple specification that does almost nothing, and we'll already see how we get constraints from this, and it's already almost not fit on the slide. All right. Basically, here's the approach in a sentence. So we're going to look at every expression and every sub-expression of that expression. We're going to assign it an SMT variable. In this case, if p then else, if p then y else set a, is assigned the SMT variable t1. And when we're going to read the solution, we're going to say t1 holds the type of the body of p, essentially. So the top level body of B is defined with an if then else operator, which has a known type. So in order to encode this type, we take, for example, in this case, the polymorphic type, any alpha, bool alpha, alpha to alpha, and we walk through the arguments of B, and we encode each of these arguments the type that the operator says the argument has to have. So for example, P will have to have type bool, Y and set alpha will have to have type alpha, and the entire expression will have to have type alpha. And here, in this case, we use the variable C1 to represent the type of alpha because we don't know what alpha is at this point. And we use bool for T2 because P has to be a boolean. Next, we just walk through the arguments. For example, P and Y, they're handled in the same way. One is a constant, one is a variable, but at the type inference level, those there is no difference between the two. And each constant and variable gets a pre-assigned SMT variable, so that anywhere in the specification where we use P, we use the same type variable to refer to it in the encoding. For the set constructor, the story is similar to the if then else. Set constructor is a built-in operator. It has a known type, takes one argument, creates a set. So the process is very similar. So T4 has to be a set type. T5 has to be the type of the content of the set. And because alpha is, again, unconstrained at this point, we use a fresh variable C2. Then we move to A. A is a user-defined operator, so we're going to need to create a fresh instance of A where we replace the arguments of A, if A has any, correctly with the arguments passed to A. In this case, A is null array, so this isn't a consideration, but we would have to do this at this point in general. And to analyze the type of A, we have to look at the body of A. So we repeat the process we just performed on the body of B, on the body of A, but this time we're going to take, instead of T1 as the top level term to encode the body of A, we're going to use the here freshly created C3 for this particular instance of A, which might be important if A had different ways of passing parameters. So for plus, plus again has a known type. It's int and int to int, so we create the constraints that mirror that. And then we finish off by looking at x, which has the SMT variable bx, and 2, which is an integer literal, so it just becomes int. We have this set of constraints. What we do with these constraints is we pass it to an SMT solver, and the SMT solver will find that this is a satisfiable set of constraints. And our recovery will then, from the SMT model, recover the following types for all of the variables, constants, and operators in the specification. As you can see, P has to be Boolean because it's part of the if then else condition. Similarly, there's a null array operator that returns an integer, and the other ones follow from the rules of if then else. So both branches of if then else have to return the set of integers, and then the body of B has type set of integers, as does Y, because set of A has type set of integer. This is exactly what you would expect. Of course, this happens automatically. I didn't have to think about any of this. I just had to push the run button, and I got this for free. And you can see how this would work for a larger specification. The constraints would be much bigger, and it would be much harder for me to manually solve them. So such a tool would be very welcome, especially in the designing phase of a specification before it's fully completed. All right. Next, let's look at some experiments. So we took 35 specifications from the community repository you see on the screen, and we basically ran them through the tool. So here you see the benchmark sizes. The reason you see 42 instead of 35 is because the specifications highlighted in red had type errors, so we added a sort of a minimal fixed specification to the set of benchmarks to show that how you can make those specifications type correct. So we ended up with most specifications being under 200, maybe under 400, and this one outlier specification reaches roughly 11 to 1200 lines of code. And these are realistic sizes. These are the kinds of specifications you would come across in real life. So I think it's quite a representative benchmark set. So let's look at how the tool did. Good news, the tool took less than a second for the majority of the specifications, with this outlier being roughly 10 seconds for the largest 1100 lines of code specification, which is the protocol 802.16 authorization PKMB35 that you see on screen. So this benchmark set includes many other well-known specifications. It includes the Kartak puzzle that Igor showed you in his demo. Only in this case, we didn't have to manually annotate anything, and the tool still found the type of, for example, the recursive function sum to be the same type that the annotation was used. But it did so automatically without any need of user interference. But it also managed to type check infer types for Paxos and Baxter's algorithm, Bosco. Interestingly enough, Raft had a type error, which we corrected this in specification 39. So these are the benchmarks. The times look to be very good for this prototype tool. There were some quirks, some interesting side cases, let's say. So one benchmark, for example, Queen's TLA, did not type check, but for the reason that it uses queens in one instance as a sequence and in the other instance as a function, which in our type system, this is not permitted because we treat those things as separate, independent objects that you cannot sort of unify, if you will. But of course, in the untyped interpretation of TLA, functions and sequences are one and the same. So converting between the two is not really converting. So using either syntax len or the function set syntax interchangeably is perfectly valid. What you could do in our framework to solve this concrete problem is you could introduce a casting operator, in which case you would cast one of the two expressions, and you would quickly find that this is then valid under casting semantics, which we don't currently support. The other one, which is interesting, is the Dystromutex specification. And this one is interesting because it's an instance of a specification that is statically not typable, but would be correct under a sort of dynamic typing scheme. So the way these operators are set up, so li3a to li4a, guarantee that any execution will traverse them in a very specific order. So the way this temp variable is being used basically as a placeholder, as a miscellaneous, if you will, where a certain value is just propagated into the next phase instead of having to define a fresh variable for each instance. So for the phase between li3a and li4a, the temp is just being reused, but it's being used in such a way that it's not consistent typed. For example, it's initially defined to be an integer, but then at some point it changes to be a set of integers, which is not allowed in our system. And this you cannot just fix with casting. Okay, so these are the experiments. Now let's look at what happens under the hood. So under the hood, what we would want is to take a type and return a term. And it seems like this will work for most things, but unfortunately there are exceptions, and those exceptions are records. So the problem with records is there's an infinite family of records with arbitrary numbers of fields, and you want to have a finite number of terms at the SMT encoding level. So how do we solve this? Well, we solve this by cheating. So we start the process by looking at a specification, and in any given specification, there are only finitely many tuple indices and only finitely many record fields. So we take that information and we use this to modify our encoding on a specification-to-specification basis to avoid having to introduce infinitely many term constructors. And this is our encoding. So we define an abstract data type ST. Most functions are what you would expect. So you have the classic constants in bool and string, and then the function set, sequence, and fun. And then we have these special constructors for records and tuples and operators, where we use one constructor for example, all sizes of records. And that one constructor conceptually has all of the possible fields in the specification. And then we use additional analysis in the recovery phase to figure out when a record term is given, which record it actually represents, and filter out spurious fields so we don't get too big of a record type that is then unusable. But this allows us to have one constructor, and in the case of operators, finitely many constructors per abstract type family. Some examples. So int obviously is translated into int, so the value of 1 would be encoded as lowercase int. But on the other end, tuples, for example, the tuple 1 and true, are encoded with the term top, which takes more than just the two arguments for 1 and true. It takes the tuple size, which is known to be 2, int and bool, which are the types of the first two arguments, and then it takes additional arguments equal to the number of indices up to the maximal index in the specification. The recovery will then take care of making sure that because the tuple size is 2, we only recover the first two fields because those are the actually present fields in this tuple type. Okay, now let's talk about actually encoding types. So how do you do this process that I just hinted at previously? So we use the type term compatibility, the syntax that you see here on the screen, to encode that term. In this case, X represents the type, in this case, top. Let's give you an example and not a definition. So let's say you have the tuple type alpha1 int and record h to alpha2. And you're in a specification with a maximal tuple size of 4. and only 2 record fields, of which H is the second. So the encoding for this would be that T, which is the type that represents term that represents the type tau, is a tuple of size 3, because that's the number of fields tau has. But it takes 4 arguments, C1 through C4, because that's the maximal number of fields in the specification. However, only C1 through C3 have additional constraints that come from the actual arguments of the tuple type. So C1 has to be alpha1, and because alpha1 is a type variable, there's not much more we can do besides assign it an SMT variable A1 with no additional constraints. C2 is an integer, because int maps to lowercase integer. And C3 is however you resolve the encoding of the record type H to alpha2. And in our case, this is by assigning C3 to be the record type, C5, C6, because NF is 2. So we have 2 record fields, of which H is the second. Because the second, C6, has the additional constraint that it encodes alpha2. But because, again, alpha2 is an unconstrained type variable, it just gets assigned the variable A2. And this is how you would encode type tau. So you get these types that you wish to encode from built-in operators. So essentially, with the exception of user-defined operators, the entirety of a TLA specification is just a chain of built-in operator applications. So if we're able to figure out the types of those expressions, this should give us constraints for the entire specification. And operators have types ranging from simple to more complex. For example, plus has the very simple type. It takes 2 integers and it returns an integer. On the other hand, set union is polymorphic. It takes 2 sets of the same kind and returns another set of that same kind. But it could be anything. It can take 2 integer sets, or it can take 2 sets of strings, or it can take 2 sets of records. As long as the 2 arguments are of the same type, it is valid to apply set union. The particularity with the set construction operator is that here we do have an infinite family of set constructors, but that's not a problem because it's an infinite family in the type system, not in the SMT encoding. So we have 1 operator per arity, and all of them take n arguments of the same type and return a set. Now, what is interesting and different from what you might have seen is the treatment of certain what we call overloaded operators. In this case, for example, the tuple constructor. What overloaded means is that a single operator syntactically is able to produce expressions of 2 different types that are incompatible. So in this case, the tuple constructor has basically 2 types that make up its what we call complex schema. So the first one is a type that takes 2 arguments of any types and returns a tuple. And the second one takes 2 arguments of the same type and returns a sequence. And what this basically means is that in a vacuum, this operator can be used for either, but we don't know which it is actually being used for until we take additional constraints from the context. So I've already used the word schema before. Schema is what we refer to the type of an operator by. So the type of an operator is called a schema, and it's primitive if the operator is not overloaded. So the primitive schema basically declares the type variables that the operator has if it's polymorphic, and then tells you the types of the arguments and the type of the return. So x1 through xn are the types of the arguments, y is the type of the return, and this operator is polymorphic and it takes k-type variables. Or it could be a complex schema, which belongs to an overloaded operator, which is just a finite collection of primitive schemas. And we'll see later that the complex schemas are really where the pun intended complexity of solving this problem comes. All right. How do we make a constraint from a known schema? Well, we compute what is called a schema instance. And the schema instance encodes the fact that this particular instance of operator application is compatible with one of the instantiations of the operator's type. So because the operator is polymorphic in general, and any particular application has concrete arguments, we just have to make sure that the instance of this operator is typed correctly. So you can interpret this schema instance as reading a term p hat encodes the type of the result, and terms t1 through tn encode the types of the n arguments of the operator to which the schema belongs. Problem is that we have disjunctive constraints that come from complex schemas. And this is really why we need to use SMT, because SMT gives us a nice way of solving disjunctive constraints, whereas in a purely conjunctive setting, we could maybe use something else, something more efficient. However, because we're not in that setting, we have to rely on SMT solver to solve this set of potentially disjunctive constraints for us. Okay, so how do we put all that we've learned together and actually determine the types of TLA expressions? We use the similar syntax to what you've seen before to denote that a term X represents the type of TLA expression E. So the way we do this, I'm not going to give you definitions, I'm going to show you by example. The way we do this, for example, for literals, is exactly what you would expect. If you see an integer literal, for example, 42, you can just say that if it's trying to be represented by the term X, then X is an int. And that's the end of it. More complex, for example, the application of plus or any other built-in operator. In that case, we have to analyze three things. First, we have to figure out the schema instance for plus, for which we compute s plus c1, c2, x. So the return of plus, which is equal to the body of the expression we're currently analyzing, has to be represented by x. And for the two arguments, E1 and E2 in this case, we have to create fresh SMT variables C1 and C2 to represent them. And then we compute the schema instance. In addition, we recurse over all the arguments because the arguments themselves might be complex expressions, and we compute their representations as well. So we compute the encoding of E1 into C1, and we compute the encoding of E2 into C2. So for plus, the schema in question here as plus is just int to int. And it would tell us that C1 has to be an int, C2 has to be an int, and X has to be an int, as expected for plus. Okay, so the more interesting case is the one with an overloaded operator, for example. If we have the expression tuple 1, 2, we do the same thing as before, but now the schema instance is different. So because the operator here is overloaded, the schema instance is essentially a disjunction of two different things. So it's a schema instance for S1 and a schema instance for S2, where here S1 and S2 are the two primitive schemas that make up the complex schema, which this operator holds. Everything else is exactly the same, so we recurse on 1, we recurse on 2 in exactly the same way. So these two schemas, concretely for the tuple constructor, are the tuple schema S1, where we take two arguments and return a tuple of potentially different types, and schema S2, which we take two arguments of the same type and return a sequence of that type. And we compute both of these constraints for S1 and for S2, and then we just add disjunction. And here's really where the complexity of SMT comes from, if anywhere. Okay, so this is how you would do it. Of course, there are special cases. There are cases where you need to manage user-defined operators, the cases where you need to manage let-in expressions, stuff like that. I'm not going to give you the definitions for those. If you're interested, contact me or Igor, and we'll point you towards our papers. Okay, so now the question is, the thing we're doing, is it actually correct? What does that mean? So we have a theorem that says that if we manage to find a model and recover types from that model, the types we recover are sensible. And what that means is that every variable in the specification is typed consistently across all of its uses, across all of the operators. Second, all of the types that we do infer, because we infer types for every intermediate expression as well, are compatible with what the schemas accept. So for example, the schema of an overloaded operator would accept a type that's a monotype of either one, and we always get one of those as a result, as stated by the theorem. So essentially, this theorem says that the types we get back from the model are useful and are reasonable. So in conclusion, we provide you with the tools for either type checking or type inferring types in your TLA plus specifications, which you can use to make your work easier, to make fewer mistakes and catch them quicker. These tools work in practice in a reasonable amount of time and return types which we believe are useful to TLA specification designers. Thank you for listening. If you have any questions, please direct them to me or Igor, and we'd be happy to answer any of them. Thank you very much.